Hello dear students, I welcome you all in Dear Mathematics YouTube channel. So today we are again with a topology lecture. Today lecture number is lecture number 4. Okay, so I will request you, if you are new to this channel and if you are seeing first time this lecture, so I will request you please check my channel and playlist. There will be, you will see a topology lecture series. So you first see all the previous lecture, that is lecture 1, lecture 2 and lecture 3. In this lecture today we will mainly focus on three fundamental results of, means mainly two fundamental results we will focus, and one we will give some examples. Okay, the first one is let xd be any metric space. Now the first result is finite intersection of open sets are open and arbitrary union of open sets are open in X. So we will prove this result. So the first is first result, what is it saying? That if we take any finite intersection, means any finite number of open sets, and if we take the intersection of them, then the intersection of all those open sets will again be a open sets. So let us suppose finite number of open sets, suppose u1 u2 dot 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 un number of open sets, and suppose let u be the finite number of intersection, n is equal to 1 to n un, un, it will be I, from I equal to 1 to n. So we are taking all the intersection, that finite number of intersection of ui, and we are giving name that intersection as u. Now suppose u is actually empty, suppose some ui is not intersecting with any other uis. Okay, then intersection will obviously be empty. Then if u is empty, that intersection is empty, then we know from the definition day I told that phi and the set X itself will be open and closed both, and I also told you to see the result how it is open and closed both this X and phi. So hence if u is phi, then obviously open, hence proved. Now if u is not phi, our main target is if u, that is intersection, is not phi, then you have to prove that u is open. So now for the open, I have defined that any u is said to be open if we take any x belongs to u, then there must exist any r, that is radius, greater than 0, such that bx comma r, what is this? It is an open ball around x or with radius r, must be totally contained in u, then only you will be said as a open set. So now what we have, this is a definition for open set. Now what we have this u is actually intersection of I equal to 1 to n ui. Now we have to prove this u as open set. So let us take any x belongs to that u, that big U. Okay, so now since x belongs to big U and it is actually big U is intersection of all ui's, so obviously this x will belongs to all ui, that is I is equal to 1 2 3 dot 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 n, means for every I x will belong, because x is belongs to intersection, so hence x will belongs to each ui, because if you take u1 u2 u3 or all, so we are taking that x is belongs to intersection. So now 3's intersection is this part, and suppose if we take any x belongs to this intersection, obviously this x is belongs to u1 also, u2 also, u3 also. So now suppose this X is now, hence X is belongs to all UI. Now since all UIs are open, therefore there must have exist some Ri in respect to all UI, because all UIs are open and X belongs to all UIs. Therefore there must exist some Ri greater than 0 such that B X comma Ri totally containing UI. Means for every UI we will obviously have a open ball around X with radius Ri such that total ball is totally containing UI, because all UIs are open we have taken. And now we will take as one common R as minimum of all Ri's, that I equal to 1 to n. Now just think this, we here all Ri we have taken, and we have taken now from all Ri we are taking the smallest R, okay, smallest radius. Now hence this R, that now Bx comma R will definitely contain in all UIs. Can you imagine? Because we are taking R smaller. This one, suppose any bigger circle is present in U. Now obviously the smaller circle is also inside U. Okay, I think you have got it. Because if any circle is totally contained in any U, then obviously if whole circle is contained totally in U, whole ball is contained in U, obviously the smaller ball will definitely contained in U. So now we have taken R in such a way that minimum of Ri's. So obviously Bx comma R will totally contain in all UI. Hence for I equal to 1 2 dot dot n. Therefore from this what we can write? We can write this Bx comma R is contained in intersection of, since this open ball is contained is all UIs, so obviously any ball is containing all UIs implies that it will obviously contain in intersection of all UIs. Hence we can write that, see here in the upper side, that for what we have taken, X belongs to our intersection, that U, that big U, okay, and what we have got B X comma R containing intersection, that is it is nothing but it is U, so we continue U. Hence what we have proved? We have proved that for any arbitrary point X belongs to U, we have got an open ball that totally contained in capital U. Hence our union of finite intersection of open sets is again a open set. Now we will move to the arbitrary union of open sets are open in X. Now let us see for arbitrary union of open sets are open in X. Means if we take any number of open sets and if we take the union, again that union will be open in X. So let us suppose take U1, U2, U3 dot 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 arbitrary number of open sets. All are open sets. Now suppose let us define any U is union of I equal to 1 to n UIs. Sorry, I don't know, 1 to arbitrary, so 1 to infinity maybe. Or you can take union of i's, that is over I, means we are taking union of UIs I equal to 1 to dot dot, we don't know, any arbitrary, it will up to 8, also it may be tens, also it may be 100, also number of UIs may be 200, 2000, any numbers. So we are taking how much amount of UI we are taking union of them. It is not fixed, but for intersection it must be, intersection must be infinite numbers, but for union it is arbitrary. If you can take any number of open sets and then if you take the union of all, then that will be again an open set in X. Now let us prove this. It is very easy to prove. It is actually definition of open set. What we have studied, every open set can be written as the union of open balls. Okay, so now suppose U1 is union of some number of open balls, U2 is some number of open balls. Now if we take the union of all open balls, again these are actually total number of union of open balls will be again an open set. So it is actually union of all open balls from all UIs, again will give a open sets. So now that is one definition. Now other definition is, suppose we have to open this one, we have to miss, we will go with the definition. Let us take any x belongs to that capital, that u, okay, that u. So hence, since u is union of ui, therefore x must be belongs to any of ui. I don't know which ui, any ui. I belongs to 1 2 3 dot dot dot, this set actually. Since x is belongs to union, so x may not be belongs to all ui's, but x must be belongs to some of ui, because x belongs to u, because x belongs to u. Okay, so since x belongs to ui, any of ui, it may be u3, it may be u4. If x belongs to any one of ui, then obviously this x will comes to union. Okay, so hence for this, suppose x belongs to ui, anyone maybe, so maybe it ui. So obviously, since all ui's are open, so therefore there exists ri greater than 0, such that b of x comma ri belongs to, so totally contained in ui. Hence, since it is totally contained in ui, therefore we can say that b x comma ri also contained in u, because u is union of all ui's. And suppose a belongs to u1 and there are u2 u3, suppose there. So we have taken union of u1 union u2 union u3. Suppose a belongs to ui, so definitely a will belongs to union. Similarly, bx comma ri is belongs to this ui. Hence, since u capital U is union of all ui's, therefore this open ball will obviously contain in the total union. Hence, what we have taken, any arbitrary element of capital that u, and we have got that there exists open ball which contained in u, totally contained in u, and that open ball is around the x with radius ri. Therefore u equal to union of I equal to 1 to, means over i's ui is union, is open. Hence proved. Now second fundamental result is finite union of closed sets are closed, and arbitrary intersection of closed sets are closed. So now here we will use the previous results. Okay, mainly we will use the complement concept. If any u is open, then u complement is closed. Okay, we will use this result. So what is the result we have? We will use this, u open, then u complement is closed. We will use this. So now the result in the previous we have, if we take u1 u2 dot dot un open sets, in the previous results that I proved is open sets, then their intersection, suppose u dash is the actually finite intersection, I equal to 1 to n ui's is open, that I have proved in the previous result. Okay, now our target is to prove this finite union of closed sets are closed in X. Okay, so now if we take complement in both sides, suppose u dash complement is u1 intersection u2 intersection u3. Actually I am writing this one explicitly here. Okay, intersection dot 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 intersection un complement. Okay, I am taking complement both side. Okay, now since u dash is open, that I have proved, finite intersection of open sets are open, so this complement will be closed. Suppose let's give us a v, and it is what we have got, it is closed actually. And from this using De Morgan's law, what you will get, since all ui's are open, therefore, and also let me first open the bracket using De Morgan's law. You will get u1 complement union u2 complement union, means complement will come to each and all the intersection will convert to union using De Morgan's law. It is union un complement. Now all ui's are open that I have taken, okay, and so all ui complement will be closed sets. So what we have got, the finite intersection, finite union of closed set is again a closed set. That is the first part. Finite union, see, finite unions of all are closed sets, are closed. That just we have used the previous result and we have used this complement concept and we have used this De Morgan's law, and hence we have proved the first part. Now for the second part, again we will use the previous result, okay, to prove this arbitrary intersection of closed sets are closed in X, actually in X. So we will use this previous result of arbitrary unions of open sets is again open. So let us take suppose u1 u2 dot are open sets, arbitrary number, we don't know how much, are open sets. Let us suppose we take this, and what in the previous result what we have proved, suppose in u dash is actually the unions of all these arbitrary open sets, that is ui, okay, means over I. What we are taking over I means 1 2 3 4 all unions we are taking, and this unions of all open sets actually open, that I have proved in the previous result. Now if we take complement in both set, that is u dash complement is nothing but u1, let me write in explicit form, u1 union u2 union u3 dot, we don't know how much because arbitrary complement. Since this is open, u dash is open because arbitrary union of open sets is open, we have proved in the previous result. Therefore u dash complement will be, let's suppose a whole give as a v, that is closed, and use De Morgan's law and open the bracket, that is u1 complement intersection u2 complement intersection dot arbitrary. So what we have proved, arbitrary all are closed now because all ui's are open, so ui complement are closed. So what we are getting, arbitrary intersection of closed sets is actually closed sets. So arbitrary intersection of closed set is actually closed in X, hence prove the second result. These are two fundamental results in any metric space or any topological space you will get. Now the third one is actually, suppose what happens if we remove this finite, what will happens to arbitrary union of closed sets, is it closed or open? Because here we are using finite union of closed sets are closed. Suppose if we take arbitrary union of closed set, what will happen? Okay, and there one concept is in previous slide is finite intersection of open sets is open in X. Now suppose if we remove this finiteness, okay, if we take any arbitrary intersection of open sets, will it be open in X? What will be that result? So I will request you just think about this. If we remove the finite concept, since it is arbitrary, so if we in the all result of arbitrary, if we take finite number, it will have no problem because arbitrary means any number of, so finite is also true. But while in the finite concept, means while in the finite statement, if we remove the finite, if we take the arbitrary concept, then what will be the result? If we take the arbitrary intersection of open sets, will it be open in X? If we take the arbitrary union of closed set, will it be closed in X? Please check this result. Otherwise, I will give the result in the second part of lecture 4. Thank you very much.